Hello and welcome everyone. Thanks for joining me today. I'm Benjamin, part of the technical and engineering team here at Ventuer. My background is in architectural design and building science, and for more than 2 decades I've worked across commercial buildings, design-intensive architectural projects, industrial facilities, and a range of work that sits right on the boundary between architecture and hard engineering. Today's webinar is focused on acoustic louvres, what they are, how they work, and why their performance needs to be understood as an engineering system rather than a catalogue item. While I'll reference Ventuer's experience from time to time, this session is fundamentally about giving you a clear practical understanding of what differentiates an acoustic louver from a standard ventilation louver, how acoustic performance is achieved and measured, how airflow, pressure loss, weather performance, and structure interact with acoustics, and how acoustic louvers are tested, specified, and integrate into complex buildings. If you work in architecture, mechanical services, facade design, acoustics, or construction, this session is intended to give you a solid technical grounding, the kind that helps you make confident decisions, challenge assumptions, and understand where performance risk actually sits. Why do acoustic louvers matter? Let's start with the broader context. Modern buildings contain more mechanical plant than ever before. Air handling units, fans, chillers, generators, and transformers all require large volumes of air to move in and out of the building envelope. At the same time, expectations around environmental noise have become much stricter. Planning controls, building consent conditions, and environmental noise standards increasingly limit how much noise a building can emit, particularly at night or in noise-sensitive locations. This creates a fundamental challenge. Ventilation openings are acoustically weak points in the facade. Without treatment, they allow sound to escape almost unimpeded. Acoustic louvers exist to manage that problem. They sit at the interface between noisy internal plant and the external environment, and they are often the primary means of controlling breakout noise from intake and exhaust openings. But they must do this while still allowing the required airflow, minimizing pressure loss, resisting wind and weather, remaining structurally stable and durable. Balancing those requirements is what makes acoustic louvers an engineering component. At its simplest, an acoustic louver is a ventilation louver that also provides measured sound attenuation. Unlike a standard rain defense louver, an acoustic louver incorporates deeper blade profiles, sound absorptive infill materials, internal perforated liners or baffles, longer and more complex airflow paths. These features are designed to reduce the transmission of sound energy as air passes through the opening. The key point is that acoustic performance does not come for free. Anything that absorbs sound or forces air to change direction will also increase airflow resistance. So acoustic louver design is always a balancing act between competing requirements. There are 3 main performance demands that must be addressed together: acoustic attenuation, airflow and pressure drop, weather and structural performance. Let's look at each of these in turn. Acoustic performance is usually described in terms of sound reduction index, R or RW, measured in decibels across octave or 1/3 octave frequency bands. This frequency-based approach is critical. Noise is not a single number. Different sources generate sound energy at different frequencies. Large rotating machinery often produces low-frequency noise. Fans and airflow tend to dominate the mid-frequency range. Turbulence and blade interaction can generate higher frequency noise. An acoustic louver that performs well at high frequencies may offer very little attenuation at low frequencies. Blade depth, spacing, internal absorption material, performance design, and overall louver depth all influence which frequency ranges are attenuated most effectively. A single overall dB value can be useful in making initial product type selections, but acoustic louvers can be more accurately specified using frequency data that matches the noise source. We would like to take a little detour now to explore the confusing differences between sound reduction index, transmission loss, and insertion loss, and why there is sometimes a magical 6 decibel difference between these numbers. Why does transmission loss and insertion loss differ by around 6 dB for some louver manufacturers? But first, the different scales. Sound reduction index, we'll call it R from here, is a laboratory measured property of a material or assembly tested in a controlled setup, usually ISO 10140. This test tells us how well the product blocks airborne sound. Where it typically applies is to solid walls, duct walls, doors, acoustic panels, and for acoustic rated louvers tested as flat test elements, not installed in ducts. Secondly, transmission loss, or TL, is effectively the same physical quantity as R. They are conceptually identical. The difference is simply the test standard and the terminology. It's the same concept with a different test method name. When someone says TL 20 dB is essentially the same thing as R equals 20 dB under ISO conditions. Lastly, insertion loss, IL, is a measure of how much a louver in a duct reduces sound travelling down that duct. IL depends on airflow, duct geometry, and louver aerodynamics. So importantly, it is not a material property, it is a system property. It applies to ventilation systems, plant rooms, discharge stacks, air handling units, etc. It's interesting that sometimes acoustic louver manufacturers will show an approximately 6 dB difference between R and IL, insertion loss. This is the part that causes confusion in the market. IL is always lower than R. A louver is full of holes. It's free area. Even the best acoustic louver may be 30 to 50% open. A flat test for R treats a louver as if it were a solid wall with slots, while IL measures real sound travelling through a duct. R measures acoustic barrier performance, while IL measures the net effect of direct transmission, diffraction around blades, resonances, flow path, and reflection effects. The difference is often 5 to 8 dB for typical blade geometries. Many manufacturers use the IL equals R minus 6 dB as a rule of thumb. It isn't strictly correct, but it is a common industry shortcut based on typical test data. Why 6 dB? Because a 50% open louver equals 3 dB loss immediately. Additionally, diffraction around the blades equals another 2 to 4 dB. The combined effect is 5 to 7 dB reduction. So a manufacturer with R20 dB may list IL as 14 dB. This is not technically wrong, but it is not universal. The true IL depends on the configuration. This brings us to airflow and pressure drop. The second major demand is airflow performance. Ventilation systems are designed to deliver specific air volumes at defined pressures. Fans are selected accordingly. Every component added to the airflow path introduces resistance. Acoustic louvers, by their nature, introduce more resistance than standard louvers. As pressure drop increases, fan energy use increases also. Operating costs rise and carbon emissions increase. And in some cases, fan-generated noise also increases. Pressure drop rises rapidly with face velocity and is strongly influenced by blade geometry and internal layout. Good acoustic louver design aims to achieve the required sound attenuation with the lowest practical pressure loss. This is why free area, louver depth, and blade configuration matter during selection. Secondly, weather and structural performance. An acoustic louver is still part of the building envelope. It must manage wind-driven rain, drain water effectively, and withstand positive and negative wind pressures. Acoustic blades are typically deeper and heavier than standard blades. They experience higher wind loads because of this, and they are also less aerodynamically efficient and more restrictive to airflow. These factors increase drag, pressure differential, and bending moments, making wind loading a critical design consideration for acoustic louvres, especially in high wind or cyclonic regions. If stiffness is inadequate, you can see blade deflection, vibration or rattling, noise generated by wind interaction, or long-term fatigue issues. So structural design, fixing strategy, and frame performance are just as important for an acoustic louver as they are for any other facade element. Let's look at how acoustic louvers are tested. Acoustic louver performance is established through a combination of laboratory testing methods, each addressing a different aspect of performance. Acoustic performance is typically measured in accordance with standards such as ISO 10140-2. This standard is important because it gives a repeatable lab method to quantify the airborne insertion loss or reduction of a louver assembly under controlled conditions. ISO 717 is a related standard that defines how to turn detailed laboratory or field acoustic test data into single number ratings that are easy to compare and specify. We test our acoustic louvers at Auckland University in accordance with ISO 10140-2. The louver is installed into a test aperture between a source room and a receiving room. Sound is generated across a defined frequency range, and the reduction achieved by the louver is measured. The result is a frequency-based insertion loss curve that acoustic engineers can use directly in noise modelling. Many acoustic louvers are also tested for wind-driven rain and pressure loss. This performance references standards such as BSEN 13030, AS-NZS 4740 or AMCA 500L. BSEN 13030-2001 uses 13 meters per second wind speed, 75 litres per square metre of rain, and air intake up to 3.5 meters per second, and the familiar Class A to D performance scale for rain defence. For pressure loss, airflow is increased in steps, and the static pressure difference across the louver is recorded at each point. The results are presented as pressure drop curve versus face velocity. This data is essential for mechanical design and fan selection. It's important to note that strong acoustic performance does not automatically guarantee good rain defence. Drainage paths, blade overlap, and profile geometry remain critical. Laboratory testing provides controlled and repeatable results, but real buildings introduce additional variables. Wind rarely approaches a facade uniformly. Turbulence, gusting, and oblique wind angles can excite vibration or generate wind-induced noise. Facade geometry, nearby structures, and mounting depth can all influence how a louver behaves once installed. For noise-sensitive or high-performance projects, wind tunnel testing can provide valuable insight into blade and frame movement, vibration or resonance, wind-generated tonal noise, interactions between the louver and surrounding facade elements. A key part of Ventuer's engineering capability is our partnership with Insol in Invercargill. Through this partnership, we have access to the Insol wind tunnel, which is the largest open jet wind tunnel in the Southern Hemisphere. It's powered by 4 turbine fans, each with its own generator, and it gives us the ability to test louver performance at full scale under realistic wind conditions, long before we take a product for independent certification. Even with comprehensive test data, Project-specific engineering is still often required. Key areas that are typically reviewed include structural design, applying site-specific wind pressures and deflection limits, acoustic integration, coordinating louvers with silencers, plenums, barriers and plant layout, and mechanical performance, confirming airflow rates, pressure loss and fan duty, detailing and installation, avoiding gaps, flanking paths or short circuiting of acoustic treatments. Poor detailing can significantly reduce the real-world acoustic performance of an otherwise well-designed system. Here we're looking at a nice example of acoustic attenuation incorporated into the dynamic facade of this good-looking building. It's the Auckland City Mission by Stevens Lawson Architects, mechanical engineering by Thurston Consulting. One of the key requirements of this project was to provide a space that is deliberately meditative. People can feel safe and stress levels are reduced through the application of trauma-informed architecture. Part of meeting that requirement was the prevention of noise pollution from the busy inner city streets below. Using Ventuer Acoustic Louvres, any problematic noise, including that generated internally, is nullified by creating an alternative sound path. Importantly, the mechanical noise from the plant room on the top of the building was restricted from spreading and disturbing the peace of those on the lower floors. For occupants, the removal of noise-induced stress helps facilitate more rapid advances in physical and mental well-being. To support designers during concept and develop design stages, Ventuer provides selection and calculation tools that allow users to compare acoustic louver options, understand pressure drop and free area impacts, review acoustic performance ranges, and assess suitability for intake or exhaust applications. These tools are built on tested performance data and reflect the same principles used in detailed engineering reviews. They are intended to support decision making, not to replace project-specific engineering. In conclusion, acoustic louvers are a key interface between building services, the facade and the external environment. They are not simply ventilation components with insulation added. They are engineered systems that must balance acoustic performance, airflow efficiency, weather resistance and structural behaviour. By understanding how these factors interact and how performance is tested and verified, designers and engineers can make better informed decisions and avoid costly performance issues later in the project. Thank you for your time, and I hope this session has given you a clear and practical framework for approaching acoustic louvers in your work.